we come to the interesting part that we all need, which is how to use the concepts we learned so far in solving the problems. Let's start with the first simple one. We have the mass in 995 kilogram per meter cube, and we want to convert it to pound mass per feet cube. If you recall, the first drug, 1 kilogram is equal to 2.2 pound mass, and 1 meter is equal to 3.28 feet. Using this information, we know 1 kilogram is equal to 2.2 pound mass, and 1 meter cube, 3.28, all cubed. Meter cube with meter cube, kilogram with kilogram, and the answer, 62, roughly 62 pound mass per feet cube. The other requirement is to find the density given specific gravity of a substance. The specific gravity is 5.7, assuming the substance density is 20 degree, because the specific gravity listed on table B1 in elementary principles of chemical processes is at 20 degrees Celsius for the liquid or for the solid relative to the density of water at 4 degrees Celsius. So we'll use specific gravity to find the density. Density of the substance is equal to 5.7 multiplied by the reference density, which is 1000. And the unit will be kilogram per meter cube. And the answer will be 5700 kilogram per meter cube. We'll need to convert it, so we'll use exactly the same step here. If you calculate it, approximately 355.4 pound mass per feet cube. Or make it simpler and use the specific gravity in American system. Rather than use it 1000, you make it 5.7 times 62.43 pound mass per feet cube. And the answer will be immediately 355. Now it's 85. There is some difference, but the answer is essentially the same. Pound mass per feet cube. If you use number 2, then you will skip the conversion part, which makes it easier for you. And even in part A, you can say 995, and I know that 1000 kilogram per meter cube is the same as 62.43 pound mass per feet cube, and you will have the same answer. It could be 62.03, it could be 62.11. The reason for this difference is because I used 2.2, but it's actually 2.2 something, and I cut this something, and that's why you have this slight difference. The second question asks about finding the mass in kilogram of a 50 liter of gasoline if we have the specific gravity of it is equal to 0.7. And also we need to find the volumetric flow rate if we are given that the mass flow rate of gasoline exiting a refinery plant, like the one we have in Aramco, Ras Al Noura, is 1150 kilogram per minute. Starting with A, because we want the mass in kilogram, we need to use the reference density, kilogram per meter cube. 0.7 times 1000, the reference density of water at 4 degrees Celsius. This will give us the gasoline density, assuming at 20 degrees Celsius. Now we know that mass over volume is equal to density. And if we want to find the mass, then we will say mass is equal to volume multiplied by density. Density works as a conversion factor, and the answer, 35,000. And now let me ask you, is it kilogram or gram? Or pound mass? We don't know, right? Because we didn't carry out the units with us in every step. And that's the point I want to reach actually. Whenever you solve questions with dimensions like mass, volume, density, then you need to write the units every time. 700 kilogram per meter cube. And this one is 50 liter. Will you say this is kilogram? Of course not, because 700 times 50 will give us kilogram per meter cube times liter. We need to convert liter to meter cube in order to cancel meter cube with meter cube. And you see here that we have 1 meter cube is equal to 1000 liter. 1 meter cube will make it in the denominator because here it's in the denominator and we want them to be cancelled. 1000 liter. And you will cancel meter cube with meter cube, and you will also cancel liter with liter, and the answer will be in kilogram unit, which is 35 kilogram. It's heavy to have gasoline amount of 35 kilogram. And this makes sense because the container is 50 liter. And 50 liter is not that simple. If you see the bottle of water we have in our houses, something like this. Just spare us from drawing. And let's just consider a real bottle of water. The one that I have here is about 200 milliliter of water. And if you want to convert 200 milliliter of water to liter of water, then you are talking about 0.2 liter. This bottle of water is just 0.2 liter. And here we are talking about 50 liter of gasoline. So it's not 10 times of this amount, not 20 times this amount, not even 50 times this amount, not even 100 times of its amount. So we are talking about some big value here, 50 liter of gasoline. And now let's talk about finding the volume flow rate. We have the mass flow rate, which is 1150 kilogram per minute. We'll use the specific gravity to find the density, already done, and we'll put it in the denominator to cancel kilogram with kilogram. We would stop here if he or she wants the answer in terms of meter cube. But what we want to find here is the volumetric flow rate in liters per second. That's why we need to do another conversion factor. 1 meter cube is equal to 1000 liter, and we know that 1 minute is equal to 60 seconds. We will cancel minute with minute, cancel kilogram with kilogram. We will cancel meter cube with meter cube, and the answer, it's not 0.2 liter. This is a confusion. I'm talking about another example here. And the amount it flows is 27 liter per second. So we're talking about 100 times this value is flowing at each 1 second passes. So each 1 second passes, we have 27 liter, this very large amount, passing out from the refinery facility. And now, because CHE drug does not give any simple questions, let's consider the complicated stuff. We have at 25 degrees Celsius an aqueous solution containing 35% WT here. This means that this 35% is by weight or by mass. So we're talking about mass, not mole fraction, of H2SO4. Has a specific gravity of 1.2563. If I write it well, you will read it. A quantity of the 35% is needed that contains 195.5 kilogram of H2SO4. So it's larger than the value we found here before, 35 kilogram. It's heavier actually. Find the volume of the solution in liter and find the percentage of error if the ideal specific gravity is 1.8255. Let's ignore part B now. You want to find the volume of the solution, then you use the density of the solution, which is equal to density of water multiplied by the specific gravity of the solution. Notice here you can also find the density of the solution even though you use the reference density of a pure water, as long as the specific gravity is also for the solution. So here solution, don't play with us. And here 1000, and then times the specific gravity, which is 1.2563, and the answer should be 1256.3. You use the density of water with the unit of kilogram per meter cube. You say volume of the solution is equal to mass of the solution divided by the density of the solution. Just use the mass of the solution divided by the density of the solution to find the volume of the solution. Nothing hard. But wait a minute. Here we don't have the mass of the solution. So are we joking here? How to find the volume of the solution? If you notice here we have 35% weight of H2SO4. We can use 35% weight of H2SO4 along with the amount of the mass of H2SO4 in the container to find the total mass of the solution. This is the reverse of what we have done before in the previous video. We were saying, okay, you want to find the mass of A, then all you have to do is to multiply the total mass by the mass fraction or the mole fraction, here X because we have mass fraction, and then you will find the mass of the component. Now we want the total mass of the solution. All you have to do is use this mass of the component, which is H2SO4, and divide it by X, which is the mass fraction of H2SO4. 195.5 divided by 0.35. This is the total solution, kilogram. If you divide and then you find an amount that is less than 195, then definitely you are doing something wrong, because we are talking about the total mass of the solution, which must be greater than the component inside the solution. 558.57 divided by the density of the solution, 1256.3. The answer is 0.4446. Carry out the units, kilogram divided by kilogram divided by meter cube. So the answer is meter cube. We want the units in liter, then all you have to do is to multiply by 1000 and the answer will be 444.6 liter. It's not 0.2 liter like this one, and it's not 50 liter like the gasoline case. It's 444.6 liter, about 1000 bottle of waters. And now if you are given the specific gravity of H2SO4, not the total solution, and when we say solution we mean something, another component with the presence of water. So the remaining here, if this is a solution of H2SO4, then the remaining will be water in this case, which means that without even saying something, we know that the specific gravity, whoops, this is not pencil, the specific gravity of water, we know it's 1000 kilogram per meter cube. And the specific gravity now for H2SO4 is 1.8255. And here he says something, or she says something very interesting, the ideal specific gravity, which means that the volume that we want will be the ideal volume. And if we have an ideal volume, and if you have two components, then V ideal should be V1 plus V2. And in this case, we will do this step but twice now. The mass of H2SO4 divided by its density plus the mass of H2O divided by its density. If you do the calculation and then add to it the density of water, if we have 35% weight, then the remaining will be water. Multiply it by the total solution, which is 558.57. Density of water, which is 1000 times 1, because specific gravity for water is 1. The volume will be 0.47 meter cube. Convert it and then you will have 470 liter. Now, as a freshman engineer, chemical, petroleum, mechanical, this question will never be in your final exam or any quizzes for now, and it's actually an introduction to the thermodynamics course. The reason for bringing this question is to introduce you to the meaning of the ideal volume and the actual volume. We have these two volumes because not all the chemicals mixed with each other will behave ideally inside a container. If you have a polar component, for example, or especially the polar components, the components that want to fight with one another, the components that do not want the other happy, so they will fight and they will make their place, they will dominate all the container. And this is actually the case with H2SO4 and water. That's why when you add volume 1 and volume 2, the actual answer will never be ideal like this one. Just simply add them together and then you will find the answer. It will actually be something like this. There will be a decrease in volume. So if you add 10 liter of some component and then with 10 liter of another component, and these components fight each other, then the answer will not be 20. Math here does not apply. Math here is not gonna find its way to convince you. The actual answer will be something less than 20. But if the two solutions are ideal, like they are not polar, they do not fight each other, then the answer will be 20. It depends. If you want to find what we call percentage of error, because we multiply by 100, so the answer will be 5.71 percentages. This percentage of error explains how far we are from the ideal one. If you add 444.6 plus 444.6 times this percentage is 5.7, shift and then here this one, approximately 470. That's the meaning of percentage of error. So that's why we need it a lot when we are working in a laboratory. We need the percentage that describes how far we are from the ideal value. In this case, what would have been if the process was ideal, if sulfuric acid and water in terms of volume were not fighting inside a container. The general variables that determine the percentage of error are these two important variables. If we are doing an experiment, then the value that we will get is called the experimental value, say like this case, volume. But there is actually volume recorded in some resources, and these resources are trustworthy, so they do not lie. How do you know that you are close or far away from this volume of literature? Then you have to do percentage of error analysis. What you will find represents how far you are from the literature value. If you have supernatural power and then you did an experiment and this experiment was perfect, it's logic to say that the percentage of error would be 0 because you got the value, exactly the same value. So this percentage of error is very important in laboratory, in industry, in exams as well, and that's why you need to know it from now. Moving on to the next question, where it asks to find the mass flow rate of toluene if we have the volumetric flow rate of toluene, which is 175 meter cube per hour. We need to find the density, but we don't have the specific gravity in this case. So if you look to the table B1, you will find liquid toluene specific gravity at 20 degrees Celsius is equal to 0.866. Density will equal to 0.866 multiplied by 1000 kilogram per meter cube, and the answer will be 866 kilogram per meter cube. Multiply this one by 175 meter cube with meter cube, and then we need to convert from hour to minute. 1 hour is equal to 60 minutes. 2525.83 kilogram per minute. For part B, we want the molar flow rate. And if you look to the periodic table in maybe chemistry books, you will find, and even in elementary principles of chemical processes, table B1, you will find the molecular weight of toluene is equal to 92.13. And in this case, we wanted kilogram per kilomole. We want it in the bottom to cancel kilogram with kilogram. So this is 92.13 kilogram per 1 kilomole of toluene. And then we want the answer in mole per second. 1 kilomole is equal to 1000 mole. 1 minute is 60 seconds. The answer will be 456 mole per second. Now the last thing he says or she says, what did we use in order to find the answer for part A and part B? Because we started from specific gravity and the liquid or solid chemical we found is at 20 degrees Celsius. This is the assumption. A mixture of methanol and methyl acetate contains 15% by weight of methanol. Find the amount of 200 kilogram mixture in gram moles unit of methanol. Whenever you see gram mole, it's just moles. Whenever you see kilogram moles, it's just kilomole. That's the meaning. We want to find the mole amount of methanol given 200 kilogram mixture. We'll start with multiplying 200 kilogram with 15% by weight to find the methanol amount in kilogram. This is dimensionless, but it actually means kilogram of kilogram of methanol divided by kilogram mixture. That's why it's dimensionless, because we will cancel kilogram with kilogram. But the meaning here is that this is methanol with respect to mixture. And that's why when we say you multiply the total by the composition of the component, you will find the amount of the component. This is why, because we will cancel mixture with mixture. The answer, 30 kilogram of toluene. Not toluene, 30 kilogram of methanol. Methanol's molecular weight is, once again, table B1, 32 kilogram per kilomole. 30 kilogram methanol, we need to convert to moles because the answer is in mole unit. And we know that 1 kilomole is 1000 mole. The answer will be 937.5 moles or gram moles. They mean the same. If the flow rate of methyl acetate now is 100 pound mole per hour, what is the mass flow rate of the mixture in pound mass per hour? It gives us the molar flow rate of methyl acetate, and it wants the mixture flow rate but in mass unit. So that's a whole conversion we need to do. Now we can do two methods here. You either convert the mass fraction into mole fraction, and then you divide this 100 by the composition in mole fraction for methyl acetate, and then you find the mixture in terms of mole. Then you convert it using the molecular weight of the mixture, which is a long story. So you will need, in that case, to find the mole fraction and to find the molecular weight average, and then you find the total mass of the mixture. The short story, though, is if you take this one, 100 pound mole per hour, and then divide it by the balance of this 15% weight methanol. The balance means what? If this is 15% methanol, then definitely if we have binary mixture, then the remaining will be 0.85 of methanol. And now we cannot divide, because this is mole and this is mass fraction. Easier to convert this one into mass flow rate first. So you will say 100 pound mole per hour. You will have the molecular weight of methyl acetate in the table, which is 74 pound mass divided by 1 pound mole. You will cancel pound mole with pound mole, and then you will end up having 7,400 pound mass. Once you have this pound mass per hour of methyl acetate, here is actually methyl acetate. Once you have the mass flow rate of methyl acetate, you divide it by the mass fraction of methyl acetate to find the total mass. If you do that, then the answer will be 8705. There is a slight difference. Maybe you see it 8710, 8715, 8705. The most important thing is that it is 87. Okay, and then it will be pound mass per hour, and it has to be greater than the component inside it. This will be the final answer. Just a quick recap: we took the 200 kilogram of the mixture, multiplied it by the amount or mass fraction of methanol to find the amount of methanol, and then we convert this amount of methanol into moles of methanol using the molecular weight. For part B, we had the flow rate of methyl acetate, and in order to find the mass flow rate of the mixture in pound mass per hour, we needed the weight percent or mass fraction of methyl acetate, which is the balance for methanol, which means 1 minus 0.15 will give us 0.85 methyl acetate. This cannot be used to divide by 0.85 because this is mass fraction and this is mole flow rate. So we needed to convert to mass flow rate. We found the mass flow rate, we divided by the weight percent, and the answer is 8705 pound mass per hour, mass flow rate of the total solution that we wanted to find in the first place. Next question. Is that it? Let me try again. There you go. Convert degree temperature of 85 Fahrenheit to degrees Celsius. Temperature in Fahrenheit minus 32 divided by 1.8, about 29. In Saudi Arabia, this is not hot actually, this is cold for us. We go out and drink tea with this temperature, degrees Celsius. For B, minus 10 degrees Celsius to Rankine. Temperature in Kelvin is just the degrees Celsius plus 273.15, 263.15 Kelvin. Use this now to convert from Kelvin to Rankine because we don't have a direct equation from degrees Celsius to Rankine. And the answer is 473.67 Rankine. What we found here is the equivalent temperature, the degree temperature. But if he asked or she asked us about the interval, then we know that 85 degrees Celsius for an interval, it's also written delta T, not exact, specific. 1 degree Celsius interval is the same as 1 Kelvin interval, and so the answer will be 85 Kelvin. Intervals make our life easy. For part D, divide by 1.8, 83.3 degrees Celsius interval. It's more likely to make it 83 because we are talking about interval. There is no decimal interval. You have to put an integer number, let's say. Okay, we have 2600 millimeter mercury. We need to convert it to PSI. And to do that, we need the first drug conversion. 1 atmosphere is equal to 760 millimeter mercury. Put it in the bottom to cancel mercury with mercury for each 1 atmosphere. Is equal to 14.7 psi. The answer 50.3 psi. For part B, make it here. 3 atmosphere to Newton per centimeter squared. If you recall, Newton per meter is what we call Pascal. So we need to convert from 3 atmosphere to Pascal first. 1 atmosphere gives you 101.325 Pascal. So you will cancel atmosphere with atmosphere, and the answer should be very, very large because the unit is very, very small. Pascal, which is equal to Newton per meter square. Convert from meter square, the compound unit, to centimeter square, so make it 100 all squared, centimeter squared. Cancel, and then you will have the answer in Newton per centimeter square. Is it centipascal? I don't think that there is a name for this one, but make it Newton per centimeter square. The answer is 30.4 Newton per centimeter square. We did it in one line. Good. It asks us about finding the 25 psi, and this is not a typo, by the way. There is actually G here. 2 millimeter mercury gauge. The meaning of psi G, it means psi gauge, and the answer approximately 2053 millimeter mercury gauge. For part D, all you have to do is P absolute minus P atmospheric, which is equal to P gauge, minus 435 millimeter mercury gauge. We can also say 435 millimeter mercury, positive vacuum. What you and I solved here will be used and will be memorized. I cannot say you will use all of them, but you will use 95% of them. And if you remember it by now, it will make your life easier. Next video, I will talk about material balance.